Right. So what we'll talk about today, or the main topic after we look past announcements and questions and so on, is series solutions to differential equations, which actually I think is pretty cool. It's in some sense not very hard. You essentially just take a series, you substitute it into a differential equation, and then it's just really a bit of rearranging and algebra. And it's not even that hard of algebra. The big thing to tackle that might be a little difficult is just being comfortable with series notation and rewriting indices and that sort of thing. But other than that, the overview is just taking a series, substituting it into a diffeq, rearranging, and that's essentially the big idea. And it's kind of neat how that it, in some sense, works so simply. But let's, like usual, start with some announcements and questions, and then we'll get into the series solution topics. And if you want to find what the period is, you just want to find the time it takes to go from peak to peak. Now, how do we do that in this case? Well, what we could do is we could just look at all the given values that they have. For instance, the applet, it sets M at 1 kg, it sets C at 0 kg, and it sets K, I guess, is totally fixed, you can't mess with, and that looks like 4 pi squared. Or this should be kg per second. And you can now just go ahead and, if you want, substitute this in to look at a characteristic polynomial and so on. So for instance, you would have x double prime plus 4 pi squared x is equal to 0. That'll give you a characteristic polynomial. Of course, of PR is equal to r squared plus 4 pi squared. And that means, if I move this up a bit, that we have roots of what? Plus and minus 2 pi I. And then we get a, let's say, complementary solution that's going to be some C1 cosine of 2 pi t plus C2 sine of 2 pi t. And now we can see that the period is going to be just how long it takes to go from 0 to 2 pi in the argument here. And that's just going to be t is equal to 1. So t naught is 1, is equal to 1 is the natural period. And just let me double check. Yeah, once the natural period. Now, if you want to get the, let's say, part B, the period of the, let's say, the wall motion, if you will, what they're looking for there is simply looking at 1 over the frequency. And the f of 0.1, actually, I'd written it as 1, but it should be 0.1. So if I jump to the next page, we have, it tells us that we should input a frequency of 0.1. And we know that period and frequency are related. Period is 1 over the frequency, and vice versa. So this is the wall, what's it calling? Support walls motion, I guess, because this is attached to a wall, so we call it like the support wall because it holds it. So you can get the period that way. And then, yeah, that's essentially A and B. Part D is asking, well, C, you just want to compare the two in your own words. D is adjusting M and F so that what you get is that graph that was shown that I put over here, or what it shows more clearly. So I want to check, does this make sense what I said? I sort of had to orient myself with what the problem was asking. Is it clear what I was going over, or are there other questions? Okay, cool. For those of you responding in chat, I appreciate it for the feedback, so I'm not just talking to the void. All right, with that, let me check back. Yeah, someone asked the Wallace period, it is just 1 over the frequency, yep. Where that frequency is the 0.1. Let's see, so someone also asked another question. How to tell the characteristics of Taylor series at a point, like we had on yesterday's. So someone asked how to tell the characteristics of Taylor series at a point. Maybe if you could clarify a little bit more, that might be helpful. I'm not totally sure what you're asking in that case, but I'm happy to go over it more if it's with some clarification. All right, while I wait for the clarification there, why don't we go ahead and at least start looking at the concept of series solutions to diffie q's, and we can always come back to the questions that you guys have. Now, the idea is going to be this, is we're going to take a diffie q. In particular, we'll look at second degree differential equations, or second order. Something of the form, let's say, a sub 2 of x, y double prime, plus a sub 1 of x, y prime, plus a naught of x times y is equal to 0. From here, what we'll actually do is we'll suppose that there's a solution that looks like a series. So we'll suppose there is a solution that looks like this. It looks like y is equal to just kind of the most general series. We have, let's say, a sub n, or sometimes I might write it c sub n, and goes from 0 up to infinity. And then we have x minus x naught. Now I want to say for a moment, we're used to seeing solutions of the form, this is just an aside, but we're used to saying solutions of the form y is equal to cosine of 2x, or y is equal to e to the x over x squared plus 1. Things like this, namely solutions made up of exponentials, trigonometric functions, and polynomials. In particular, we certainly have never seen an infinite number of terms in a solution before. But what we get here is indeed just a polynomial. If you imagine, let's say, writing this out, I'm going to erase this. Imagine writing this thing out, and what you get is something like this. You get, and this should have an n up here. Missed that. You get a naught plus, let's say, a1 x minus x naught, where I should say x naught is an element of the real numbers. It's some fixed number. But we have this here plus a2 x minus x naught squared plus a3 x minus x naught cubed. Well, this is just some polynomial. has an infinite number of terms, but it's a polynomial nonetheless. So what we're really looking at is polynomial solutions to differential equations. So even though there's an infinite number of terms, it's not really anything different than what we've seen before. Moreover, because we have an infinite number of terms, it's possible that we could end up with something that could be rewritten as not a polynomial, but something else. For instance, if we chose x naught to be 0, and we chose the ANs to be specific values, and this again is just kind of an aside, if we ended up with y is equal to, say, 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, so on and so forth. If we ended up with this as our solution, well, we actually know that this is a particular Taylor series for a function that is the exponential function. We can rewrite this as simply e to the x. You may remember this or may not. I don't think it's a really big deal right now to remember it, but it could be that we get this infinitely long polynomial, or this polynomial with the infinite number of terms, and we could eventually just rewrite it this way. So it's something to keep in mind that we're finding solutions that are polynomials, and we may end up with things that are not polynomials, or we could rewrite the infinitely long polynomial and get something else. But how does this actually work? I'm going to delete this because it's, again, just an aside or motivation for what's going on with this. Really, all we're going to do is we're going to take this thing that I'm going to highlight here. We're going to take this, and then we're going to substitute into here. Now, if we do that, we're going to have to take a derivative, but that's something that we can do when we have series. We just do it term by term. Each term, we just take the derivative. It's just power rule over and over. And then we substitute it in, and we'll essentially rewrite it and match everything up. Now, I don't know that there's a nice general way that's illustrative to go through it, so why don't we just actually jump to an example right away? Well, actually, maybe I'll say one more thing real quick, and that's this. We're going to look at particular values x naught such that a2 of x naught is not equal to 0. So let me put a caveat here. This will be explained more in the singular points video tomorrow, if you watch it, or whenever you watch it. It'll make it more clear. What we'll look at are essentially called ordinary points, but for now, all we should keep in mind is we want to pick this x naught such that when we substitute in here, we don't get 0. So that's all we should keep in mind for the moment. But like I said, let's go ahead and look at series solutions like a specific example. So suppose we have this diffie-q right here. Now what we want to do is suppose there's a solution and namely that solution is y is equal to a series and let's have that be some a sub n and then x minus x naught to the n. Now here we can actually determine, we have some flexibility in deciding what this should be, what this x naught should be. We just want it so that when we substitute it into the coefficient function here, actually, let me get in the habit of using this laser pointer here. So when we substitute this into this, that what you get is not 0. But since the coefficient function is just 1, no matter what we substitute into it, we won't get 0. We'll always have 1. So we can actually pick whatever we want here. Just to keep it simple in this first instance, why don't we go ahead and choose x naught is equal to 0. But again, you could choose other places. Since we've chosen x naught is equal to 0, then, I'm just going to rewrite this a little bit. We get the series that looks like this, just an x to the n. But again, we could have chosen it x naught to be 1, we could have chosen it to be 2, and so on. But we choose it to be 0 to keep it simple. Now we're going to take this, which I'll color. Let's color it, let's say this color. We're going to take this, and then we're going to find the derivative and then the second derivative so that we can substitute it in. Because right now what we have is this y, which looks like this. And now we want to find this y double prime. And then we'll substitute it in. If here is y, we'll compute y prime. Y prime is going to be equal to n a to the n x to the n minus 1. And because when n is equal to 0, we don't have anything, like it will cancel the term, what we'll write is n is equal to 1. Though you could put n is equal to 0 there. That's not technically right, but yeah, no, it's best not to do it because you get x to the 1 over x, which is not actually what you would have, even though the 0 would kill it. But just be careful about your starting index there. If we take the derivative one more time, what we end up with is, in a similar way, the following here. And this is just by using the power rule. Now we'll take and substitute. Y is turned into this series. Y double prime is turned into this series. So let me put this on another page. So if we have y double prime minus y is equal to 0, that's like saying this is equal to 0. And actually, let me erase this. Okay, now at this point, you can do the rearranging here, or if we wanted to, I'm gonna jump back, we could have done the rearranging back here. Either way, it doesn't really matter. I think I'll try to do both just so you can see both ways. But it's just a matter of when you choose to do the rewriting. But what you want is at some point to have all of these be written with the same exponent. That's going to make combining them much easier. So after you substituted or before you substituted, either way, you want to rewrite these so they have all the same exponent. That is, I want, if this is x to the n, this to also be x to the n. Or correspondingly, I could have them both be x to the n minus 2. It doesn't really matter, except that you just want them all to be the same. And maybe I'll note that here. So the next step we're going to do is to rewrite these so that they have all the same exponent. And I think I talked about this in the Taylor series video. I hope I did. But what we want to do is rewrite this so that it has x to the n term or factor here, so that it matches up with this x to the n. If we do that, what we'll get is, let's see, n is equal to 0. And if this isn't clear, just let me know. We can talk about it more. N plus 2, n plus 1, a to the n plus 2, x to the n. And everything else over here stays the same. So what did I do? I took, let's see, how do I want to highlight it? I took this and I rewrote it. Took this, rewrote it. This, rewrote it. This n, rewrote it. And this n minus 2 and rewrote it. Notice I subtracted 2 from the starting index value, n is equal to 2 to n is equal to 0. And then to compensate for that, I added 2 to each instance of n. So n went to n plus 2, n minus 1 went to n plus 2 minus 1, and n plus 2 again, and n minus 2 went to n plus 2 minus 2, which is n. And now we have what we want. We've got x to the n here, we've got x to the n here. So we've got all the same exponent. Now that'll make it easy for combining these things. In particular, what we'll do is we'll start by looking at n is equal to 0. Now both of these start at n is equal to 0. So what we can do is say, well, they start at n is equal to 0, then they'll also both have an x to the first or x to the n is equal to 1 term, and so on. So actually what we could do is combine this into one big series. Sometimes you can't combine everything into one big series right away, but here we can. That's because they start at the same index value, so we can just combine their terms that we're adding up. If we do that, we combine their terms, it's not going to be anything really crazy. We're just going to say add this thing to this thing. Or maybe put it another way, we're going to add this to this. If we do that, what we get is n plus 2 times n plus 1 an plus 2 minus an, and then all gets multiplied by x to the n. Now, just to check if this is making any sense, or just see how you guys are doing, just so I'm not, kind of talking and thinking that I know what's going on, and maybe you guys too, to actually see where you're at. If you're following up to this point, if we compare the left-hand side to the right-hand side, the right-hand side, of course, we have 0. That means that this thing should be 0. Based on that, it's not very complex, so maybe don't think about it too hard. What can I say that this coefficient should be? If you maybe type in chat, if you're not sure, that's okay, but just to kind of check. Okay, for those of you who put something in chat, I appreciate it. In fact, it will be a constant, and for those of you saying 0, it will be equal to 0. And just to double check, the reason why is on the left-hand side, we do have a polynomial. So let me put this over on the other side and then expand it. And this is really the key idea of this method here. If I take this and I rewrite it, what we would have is, starting at n is equal to 0, I'm going to try to write this small so I can fit it. We have 2 times 1 times a sub 2 minus a sub 0. That is multiplied by x to the n, or x to the 0. So that's just it. Then we get, for the n is equal to 1 term, we get 3 times 2 a sub 3 minus a sub 1. That's times x to the first. And then n is equal to 2. So on, we get 4, 3, a sub 4 minus a sub 2 times x squared, and yada, yada, yada. Now, the only way a polynomial can be equal to 0 is if all of its coefficients are equal to 0. So this whole thing being equal to 0 means each one of these need to be equal to 0. There's no way you can combine x and x squared to cancel each other out. You need to individually have each of these coefficients be equal to 0. So what we have is this is equal to 0, this is equal to 0, this is equal to 0, and that's true for all of them. All right, well, what does that tell us? That tells us that we can get I like to think of it as a chain between these different coefficients. Now, it's maybe worth kind of reflecting back and saying, what are we doing here? It may just seem like a bunch of notation, but to remind ourselves what we're trying to do. Flipping back, what we said is we suppose there was a solution that looked like this in general. We chose to center the solution around 0. That means that if x naught is equal to 0, we just get this. Now we're saying this thing is the solution. Here, or in the specific case, x naught is equal to 0, this one. We'll know exactly what this looks like so long as what we have are these here, these coefficients. What we're trying to find is exactly these. So we're trying to find these. If we know what they are, we know everything about the series. The only thing unknown with the series are these values. Otherwise, you're just taking, x to the 0, x to the 1, x squared, x to a third, and so on. So you know what's happening with these x and exponents. You're just not sure what these constants are. So once you know those, you know the whole thing. So if you can find those out, you'll know everything about your series and then hence your supposed solution. So we're trying to find what these are. If I flip back to our latest work, we're here. Now what this gives us is a chain. If I take the very first part here, what we'll notice is that a naught divided by 2 is equal to a squared. How did I get that? Well, I just looked at this equation. This is equal to 0, and I just did a little bit of division, and we get this. At the same time, let me jump ahead and note that here, what we have is also that a2 divided by 3 times 4 is equal to a4. And then I don't think it's very hard to convince you, or I don't think, I think you would see that you could also get a relationship between a4 and a6 when you look further down with the x to the 4th term. And this creates what I like to call a chain. So based on this, you can imagine that you start with a naught. If you know what a naught is, what you get is a sub 2. And you can just compute it by taking a naught divided by 2. So this is a naught divided by 2. Then, once you have a2, you can get a4, because that's simply going to be a2 divided by 3 times 4. And then a4 will give you, of course, a6. a6 will give you a8, and so on. I'm going to erase this to move it up. Now this gives us all the even index coefficients. But what we would like is every single coefficient. So now we just need to know how to get the odd coefficients. But you probably already see, guessing you're maybe ahead of me here at least, we can take this equation, this relationship, and now we say once we have A1, that will tell us what A3 is, because A3 is simply A1 divided by 3, or maybe 2 times 3. A3 tells us what A5 is. That's just going to be A3, let's see, 4 times 5, which will tell us what A7 is, and A9, and it just keeps going. So you can get every single coefficient as long as you know A0 and A1. So what we could do is we could actually rewrite this whole series in terms of, well, not this series, but actually flipping back, rewrite this whole series in terms of A0 and A1. And actually, those are special values that are worth tracking. They're not totally unknown to us. So if we said the solution is this here, which I'm going to change to white just since we're not substituting it, we can write this out as A0 plus A1 x to the first plus A sub 2 x squared plus A sub 3. Maybe I'll do just a few more. So this is how it's going to look in general, but now we know what these values are, or we know a general pattern for them at least. If I say that A0, I'll color maybe magenta, I'll color A1, say yellow. We can rewrite this. Well, the first part's not going to change. But then A2, we know what A2 is. Jumping back, we said that A2 is going to be A0 divided by 2. So now we can say that this is A0 divided by 2, and that's x squared. And then from there, we've got A1 divided by 6, because that's 2 times 3. That'll be x to the third. Then we have A0 divided by, let's see, 2 times 3, 3 times 4 is 12. And you can see the pattern here. Let's see, 3 times 4, 4 times 5. No, that's not right. I've done something wrong. These are fine. This actually is not quite accurate. These need to be changed, these values. Let me rewrite those. So this is actually A2 divided by 3/4, which is, or divided by 3 times 4. That's A0 divided by 2 times 3 times 4. This A3 is A1, 2 times 3 times 4 times 5. Okay. And if I now substitute appropriately, we're going to have A0 2 times 3 times 4. So A0 2 times 3 times 4 is 24. And A1 is 6 times 20. So it's going to be 120. There we go. And then, of course, you can just keep doing this to find A sub 6 and A sub 7 and A sub 8 and so on. Now, this may not seem maybe super great because we still don't know A naught and A1, but I claim they're things that we, in many cases, would know, or there's a certain form to them. If for a second, and actually, let me, before I go on, to say what those are and check in with you guys. Is this making sense what I'm saying so far, or are there questions you have about this? I don't want to rush past if maybe there are any questions. So my first question to you makes sense, or? If it doesn't make sense, any questions you want to ask at the moment? And if you're just absorbing it and it's, a lot of information taken at once, I understand, that's okay. Sometimes it can even be hard to know what questions to ask. And yeah, someone asked, could you denote these with, factorial values? And in some cases, yes, in some cases, no. Some cases you'll kind of skip around. If I'm looking at this, I think you can use factorials here. I'd have to double check the next term or two, but I'm pretty sure that will work. Just don't quote me on it, but I'm 99% sure that, yeah, you could write these just as in a factorial form. So you don't necessarily have to multiply them out, but like this. Okay, so for those of you who put something in chat, I appreciate it. Giving me some feedback so I know what's going on with you. I'll now say that we can find A naught A1 in the following way. Imagine you have, well, just this y up here. If you take and you substitute in 0 for x, if you take, and here's a chance to kind of just check that you see what's going on with the different series, at least just, inputting values and know a little bit about working with it or test yourself in that way. If you take y of 0, that is substitute in, y of 0, substitute in x is equal to 0 up here, what will it give you? If you want to say in chat what you think. And if right or wrong, doesn't matter, just what do you think? Y of 0 is equal to what? We can say it's equal to something. What should we say it's equal to? Okay, for those of you who put something in chat, I appreciate it. Indeed, you're going to get A naught. Simply because all these terms have an x. So when you take 0, you'll get 0. Likewise, imagine we took y prime of 0. Y prime of 0 will be, if we differentiate all this, it'll be A1, or I should say, if we just start by taking y prime of x, it's going to be A1 plus 2a2x plus 3a3x squared plus 4a4x cubed. And now if you take y prime of 0, again, just to kind of check yourself, what's y prime of 0 going to be equal to? Yeah, okay, good. Yep, for those of you who put something in chat, thank you. Indeed, it's just going to be A1. Now, how is that nice? Well, when we have, and I'm going to flip back, when we have diffie-q's like this, we can find their general solution formula, or if we have initial value data, which would be y of 0, y prime of 0, then we can actually find the explicit solution. And that's essentially exactly what we have here. Before we called it C1, C2, if you will, for the parameters. But these are nonetheless just parameters. If I even, let's say, change this part to be white, so that we really just focus on the A naught, A1 parts, this is just two parameters. You could write this another way, and I'm going to remove this for the moment, but if that made sense, we'll come back to it. But notice that you could take everything with an A naught in it, and you get A naught times a thing, which is 1 plus 1 over 2 x squared plus 1 over 24 x to the fourth, plus all the even degree terms. Then we have plus a1, and I guess you could even factor an x, but we don't really need to. We have x plus 1/6 x cubed plus 1 over 120 x to the fifth. And notice it's a second degree or second order differential equation, and what we get is a solution that has two parameters. We've called it a0 and a1, but this is like your C1, C2. And in particular, we can even rewrite it so that it looks like this, so that it's y of 0, once you know that, and then you can say y prime of 0. So once you have the initial value data, you can exactly write what this is without any hesitation. Which you can't always do for C1, C2. Sometimes you have to do a little work to find what those are. Okay, and that's essentially it. Now, as I mentioned before, it could be that this is equal to some function, but like, this is a function, but it could be an exponential or trig or something like that. But we don't necessarily, in this case, need to be able to figure out what that function is at the moment. This is what we're looking for at the moment. It's just the solution here. Now let's maybe go through another example, just because more examples are helpful, and we'll do one that's a little bit more complicated. This is maybe an easiest case because we're not actually multiplying by anything other than just constants, just 1 and -1. But let's say we have something in front of here that is some function that's not just a constant. So we have some non-constant coefficient functions. And here, I think maybe this one's a little too easy. So let's do one that's a little harder. So you guys have a hard example that you can reference back to, or not that hard, but a little bit harder. Let's suppose y is equal to the following. Is the solution. Now we have a choice for x0. I'm going to choose x0 is equal to 0 again, though you could choose x0 is equal to a variety of things, so long as the x0, when it's substituted into this coefficient function, does not give you 0. Let me change this coefficient function for a second. And then let's just write it as x squared. We'll go back to x squared plus 1, but just so that you see an example of how it works. If this was my differential equation, what should I not choose x0 to be? Oh, it's so ironic. What should x0 not be? What do you guys think? Okay, for those of you who put something in chat, thank you. And indeed, it should not be 0. And that's because if you substitute in x is equal to 0, you'll get 0 here. Correspondingly, let's say I change this a little bit so that we had x squared minus 1. What should x0 not be? So what should we not put here? It's actually two values. Okay, for those of you who put something in chat, thank you. Indeed, it should not be 1, nor -1, either one of those. In this particular case, so the last question for the moment, what should x naught not be when we have this as our coefficient function? So what should x naught not be if this is the one we're looking at? And if you're not sure, I claim you definitely know it, even if you don't think you do. You just ask yourself, what real number can you substitute into this function and get out 0? And the answer there, of course, is, well, there's no real number that'll work. I would work, or -I, but we just want to focus on real numbers. There's nothing saying you couldn't look at complex numbers, but we'll restrict ourselves to real numbers here. So there's nothing that wouldn't work. That means any real number would work. So x naught can be anything in this case, because no real number substituted into this will give us 0. Therefore, if we choose x naught is equal to 0, that's going to be fine in this case. Now I should say, we could also choose x naught is equal to 1. I'm not going to do that because this is already going to be involved enough. Like there's just going to be a lot of notation and writing. So I don't want to muddy it up by also putting x naught equal to 1. But if you put x naught is equal to 1, nothing much would really change besides the fact that you would have, I keep forgetting to write, besides the fact that you would have x minus 1 to the n instead of just say x to the n. And someone asked, can series be used to solve any second order homogeneous differential equation? You can certainly do it if your coefficient functions are polynomials. So notice here we have polynomial, polynomial, polynomial. The problem is if you had, let's say, cosine of x as one of your coefficient functions, that wouldn't gel with the series form because the series is just a polynomial, power series. And what you're doing is you're multiplying by more polynomials, so you still have a polynomial. But if you, let's say, had cosine of x or something here, you then would have trig times polynomial. Unless you wanted to rewrite the trig function, use it as, its Taylor expansion, which you could do. I guess you could do that. But then it would become a lot more involved. So as I say, certainly if these are polynomials, that's how we'll look at it, where each of these coefficients are polynomials. And in another case where they're not, you could, I haven't tried it, but you could write the Taylor series expansion of that function, which will just be a polynomial. But then it's just going to be a real mess because you're multiplying infinite series. So you got to think about how you would multiply two polynomials with infinite number of terms. You can do it. It's just going to be a little bit messy. In fact, when I say a little bit messy, I mean a lot messy. Another question is, are we going to be able to use x not equal to 0 for all of them? No. If the answer to that, yes, no. If you have x squared, y double prime, for instance, if this was just x squared, then we could not use that one. And if I get time to, we'll do an example, but probably not. But if you're struggling with one where it is not equal to 0, you can certainly let me know, and I'm happy to go over it with you. But I claim it's actually not too hard. If you understand that x naught is equal to 0, 1, then it's not too bad. But yeah, if you're having trouble with that in the future, I'm certainly happy to help you out. But let's do this one quick so we get through it. So we're going to suppose we have x naught is equal to 0. That gives us, like before, this series. For the sake of time, maybe I won't color it. But if you really want to see that color to see what's going on, let me know, and I'm happy to do it. But just like before, we take derivatives, and we get this. Then we get this. Now I'm going to take and multiply each one of these by their respective coefficient function. That is the 2, the negative 2x, and so on. Multiplying y by 2, or saying 2y, that's simply going to be equal to the series, which is 2a sub n, x to the n. Then we're going to have negative 2xy prime. And again, if you have a request for color that is just a little too hard to follow otherwise, let me know. We've got negative 2n, a to the n, x to the n. Now, why did I put x to the n? Well, we have x here, and then we have x to the n minus 1 here. If you multiply those together, of course, you're going to get x to the n minus 1 plus 1, so you get x to the n. So that's from this. Likewise, if we do x squared plus 1, y double prime, what we'll get are actually two series. First, you're going to get n minus 1, a to the n, x to the n, because we've got x squared times x to the n minus 2. Then we're going to have plus the series is equal to 2 n minus 1, a to the n, x to the n minus 2. And maybe I'll move this over here. Now notice, actually, we have x to the n, x to the n, x to the n. The only place where we don't have x to the n is with this one. So I'm going to go ahead and just rewrite this series here so that we get x to the n here. If I rewrite it, what we get is this. We are going to set this to 0. We're going to add to each one of these. And then now we'll get x to the n. And this is what we want. We want all of the exponents, actually here, 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 here. We want them all to be x to the n. That's good. Now we can take this, substitute it into this differential equation, and then rearrange. Now I actually will color this. Otherwise, it's just be very difficult to keep track. About there and here. Now let me actually take these, copy on the next page. I'm going to put this, this, this. Right, this is yellow. This is cyan. This is magenta. And now I can write it this way. And now this is a Diffie Q such that all this is equal to 0. Let me jump back and just put this label. Now let me double check. Did I? this is equal to 2. Okay. Now, since all of these exponents are the same, it's all x to the n, what we're doing is we're essentially looking at the indices and pulling from the individual series as they match up with the indices. For instance, and I'm going to ask you a question in a second. If we have n is equal to 0, if there's series A, B, C, D, which are the series that have terms where n is equal to 0, just simply? So which series of these 4, could be all, could be one, could be none, which ones have a term that will have n is equal to 0, or an x to the 0 term, if you will? Okay, for those of you who put something in chat, thank you. In fact, it is B and D. Notice that the series in cyan here in this first magenta one, the one in cyan doesn't even start till 1, this one doesn't even start till 2. So what we do is we say for n is equal to 0, we take from the series here and here, and what we get is, well, n is equal to 0, so we get 2 times 1 times a sub 2 plus 2 times a sub 0. That's again substituting n is equal to 0 into this, and then n is equal to 0 into this. Then for n is equal to 1, all but the very first series will have a term like that. So then we get, let's see, 1, so we get 3 times 2 times a sub 3 minus 2 times 1 times a sub 1, and then plus 2 a sub 1, make sure I'm not crazy. All right, that's all from n is equal to 1. That gets multiplied by x to the 1. Then everything has a n is equal to 2 term. So what we can do at that point is just rewrite it as one big series. So this is going to be n is greater than or equal to 2. And I'm going to try to fit this in. So we get single series, n starts at 2, goes to infinity, and we should get n minus 1 times a to the n. That's from the first one. Then we get plus n plus 2, n plus 1, a to the n plus 2. That's from this one. Then we get minus 2n a to the n. As you can see, it's getting a little tight. And then plus 2 a to the n x to the n. Now, from the first few terms, what we get are that here, I think if you rewrite, we can say that A3 is equal to 0, because this whole thing has to be equal to 0, and these cancel. Then from this one, what we can say is that A2 is equal to negative A naught. Now from there, what we get is something called a recurrence relation. So the recurrence relation is here. And it's something like n squared minus 2n plus 2 times a to the n plus n squared plus 3n plus 2 a to the n plus 2. Since this should be equal to 0, and notice all I did was I just did a little bit of algebra here. since this should be equal to 0 here, we get that n plus 2 is equal to n squared minus 2n plus 2 divided by n squared plus 3n plus 2 times a to the n. And now this gives you a chain here. So if you know what a naught is, you can get a2, you can get a4, a6, and so on. If you know a1, you can get a3, you can get a5, a7, and so on. Because whatever an is, you can get the next one 2 steps beyond it just by multiplying by this number.
To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.